And with respect to the flow of electron in different mediums, we have to derive boundary conditions for dielectric medium, as well as for conductor dielectric medium, as well as conductor free space medium. Okay, so before going into the concept of deriving the boundary conditions, we have to see some of the basic concepts that are required to understand how to derive the boundary conditions. So for that, so we have seen resolving the components, which are having a vector, how to resolve with respect to x-axis and y-axis. Here we have taken how to write by two components. So where x is parallel component and y is normal component. So here we have to apply for boundary. So the component which is in parallel with the boundary, we are going to call it as tangential component, which is nothing but our x, and the component which is in normal to the boundary, which is called as normal component, which is nothing but ey. So transforming these two components with respect to the boundary conditions, I have written that is E is equal to tangential component plus normal component. Similarly, I have applied for electric flux density, that is D. We will perform the analysis of the flow of electron by having the condition for E as well as for D. And just we have recollected some of the concepts of electric potential. So where we have applied for electric potential for a closed loop, since it is a closed loop, obviously we will have as a short circuit where the voltage will become zero. So therefore, earlier equation is VB, which is equal to minus integral A to B. If it is closed loop, so therefore I have taken as closed line integral. The final value is equation 1, that is the closed line integral of E dot dl is equal to 0, where in order to have the analysis on electric field intensity, I will make use of this equation. And now later we have electric flux density. So as we have already done many times in applications of Gauss law, the same derivation again I have done here. So where we have obtained enclosed is equal to closed surface integral of d of s. So remember that while deriving the conditions for d, so definitely we have to consider the surface as closed surface. Unless until our consideration, the whatever the area that we have considered as closed, so we can apply the Gauss law. If and only if the surface is closed, then only we can apply Gauss law, and hence I have written as Qn plus d is equal to closed surface integral of d of s. And these are the summarized parts, part 1, part 2. I will make use of them. So finally, so we have gone with the dielectric boundary conditions. Just I will draw, don't worry again. So first I will have, see, this is an empty page. So if you want to make two regions, okay, so definitely I have to draw one line. So that line will act as a boundary for top of the page as well as bottom of the page. So therefore here I'm making one boundary. So where we are considering the upper part, so let it be dielectric medium. So whose value is given as epsilon 2, and lower part is also the dielectric medium whose value is given as epsilon 1. So therefore these are two different dielectric mediums because they are having different values of epsilon. Okay, so now what I have to do, so I have to consider, so first of all I'm going with electric field intensity. So I'm going to have the boundary conditions for E, which is nothing but what? Electric field intensity. So since I'm taking the electric field intensity, what I have to use, the equation that I have to use is, so closed line integral of E of dl, which should be equal to 0. So if the equation has to be satisfied, that value is equal to 0 unless until I have to consider what? One closed line, or simply we will call it as what? Loop. So closed line, or just wait. So closed line, or we can call it as a loop. So that's the reason why I'm considering one loop. So here I'm drawing one loop since our intention is to understand the behavior of flow of electrons in both the mediums. Suppose if I consider the loop only in only in the dielectric material of one, then we can know only the behavior of flow of electrons with respect to this dielectric medium only. If I consider only the loop inside of dielectric material 2, then we can understand the flow of only with respect to dielectric medium. That is not our intention. Our intention is, so when the electron is flowing from one dielectric material to the second dielectric material, then how it is behaving. So that is the reason I'm considering the loop, whatever the closed loop it is there, whatever the closed loop. So I'm considering half part in one dielectric material and remaining half part in second dielectric material. Okay, so I'm giving, since it is a loop, so definitely we have to give its direction, as I told in case of Stokes theorem. For every loop, we have to give a direction. Either you can go with anti-clockwise direction or you can go with clockwise direction. That is not, there is no such protocol that you have to consider only clockwise. You can go with anti-clockwise also. Now I'm naming the loop as A, B, C, and D, and I have taken the height of the loop as delta H, so that half of the loop is present in medium 2 and remaining half part is available in medium 1. So therefore I have taken H by 2 and H by 2, and the width of the loop I have considering as delta W. Delta W. Total height is delta H. Okay. So now what we have to go with? E. So now E is nothing but what? So if an electron is having, for an electron, definitely because of that electron, you are having the field around it and it is having some intensity E. So I am drawing, let it be one electron. It is coming from dielectric medium of 1. So therefore I am writing it as E1. And now it is entering, after crossing the boundary, it is entering into dielectric material of 2. So here I am giving the notation as E2. And we are resolving the components. So we resolve E with respect to a boundary. So that is E will be equal to Et plus of En. Okay, so E will be equal to Et plus of En. So now I am going to draw that the component which is parallel. So boundary is like this. So let us consider. So let us take one parallel line with the boundary. So this will be the parallel line with the boundary. So since it is parallel, obviously we will call it as a tangent. So therefore this will be E1 T and this will be E2 T. And next it is we go with normal, that is nothing but perpendicular to the boundary. So this is perpendicular to the boundary and this is perpendicular to the boundary. So this is, it belongs to E2. So this is E2N. Since this belongs to E1, so this is E1En. So this is all the schematic diagram. So here this is what the black color line, which is nothing but boundary. And we are assuming, we are making one assumption with respect to the boundary. What is that assumption means? The boundary is charge free. Charge free, that means on the boundary, the value of charge will be equal to 0. So this thing we have to remember later. I will make use of this condition, this assumption at the last. But here we have made one assumption with respect to boundary. What? So on the boundary, so this is the value of Q is equal to 0 on the boundary, but not inside the dielectric material. So now I'm going with the application of this equation, that is what? So closed line integral of, so closed line integral of E of dl, which is equal to L. So closed line, that is nothing but loop. So what is our loop? So loop is closed line or A, B, C, D, A. So starting from A, moving towards B, next C, next D, and again it is closing at A. So therefore, closed line can be equal to what? So integral of A, B, C, D, A will be equal, E dot dl is equal to 0. So this closed loop is formed by individual lines of AB. This thing already we have seen. Individual lines of AB plus individual line of BC plus individual line of CD as well as individual line of D and A. All together it is forming a closed loop. So therefore, so integral of ABCDA can be written as what? So integral of the line AB plus integral of the line BC plus integral of line CD plus integral of line DA. So that value is E of DL will be equal to what? 0. Will be equal to 0. So now see here, whatever the line is here, so that is AB, so which is nothing but integral AB of E of DL. This is integral of BC E of DL. So similarly, integral of DC CD E of DL, integral DA E of DL. Now I will calculate individual integrals and finally I will substitute the value in this equation. Okay. So now see here, this is the line AB. In this, if you consider a small amount of DL and if you integrate the value of AB with respect to DL, in which an amount of current is flowing, flow of current is nothing but flow of electrons. If the electron is flowing, obviously the value of E will be there. So we need to calculate E value. So integral AB E of DL for this line. So for this purpose, in order to get the value of this, okay, nothing but what? Length from where to where? From A to B. See here, from A to B, what is its length? See, in this loop, this is the value from A to B. So from A to B, what is the value? So the value is delta W. So the value of integral of DL, that value will be the total length of the loop, the width of the loop, that is nothing but what? The width of the loop is given as delta W. But here, see, this AB, see, this is important point. This AB is completely present in the dielectric medium of 2. This AB, the line AB, which is completely present in the dielectric medium of 2. So therefore, you have to see the component of second electric field intensity, that is E2. And now come back to again this line of AB. This line AB is in parallel with the boundary, So now you have to go with the tangential component, the parallel component, which is nothing but the tangential component. Since the loop is completely present inside of the electric material 2, the value of E, whatever the value of E is there, so we will write what? E2T. E2T multiplied by the width is given by what? Delta W for integral AB E of DL. Okay, see here, I am drawing here. This is the boundary. Here, we are having the loop. So here we are having AB. This AB is completely present in epsilon 2 medium. In epsilon 2, we are having E2. But the line AB, see here, the line AB is in parallel with the boundary, is in parallel with the boundary. So whatever the component of E2, we have to take the tangential component, that is called as E2T. See here, E2T and AB both are having in the same direction. So therefore, you have to consider plus E2T, plus of E2T, and integral of DL is nothing but from length of this line from A to B. What is the length of AB? So the length of AB is what? Delta W. So therefore, integral AB, E of DL value will be equal to E to T. Integral of DL is nothing but what? Delta W, which is our first expression. Please don't write anything. 236. Okay, so now we are going with the second part. So what is the second part? Integral BC E of DL. So please listen carefully. Derivation. So steps are very simple, just a matter of one step only. But you cannot by heart unless until how to write, you know how to write this equation. Okay. So first I am coming with AB. Later I am going with B and C. So integral BC of DL, that means it is nothing but the total length of this conductor BC. Okay, but here with respect to this conductor BC, okay, so this conductor BC, half part is in epsilon 1 and half part is in epsilon 2. So that is the reason. So here half part it is present in epsilon 2, that is nothing but half part is delta H by 2, and remaining half part is present in first dielectric medium, that is epsilon 1 of delta H by 2. So therefore we have to keep in our mind about this point, and later we have to come back. See here, in AB, you look for AB only. So this is the boundary and this is the line AB, sorry, B and C. Half present in epsilon 1, this is delta H by 2. So in this medium, we are having field intensity of E2. In this medium, we are having field intensity of E1. And the direction of B2 and the direction is from B to C. But here, if you see this diagram of component diagram, so these things, okay, so this thing I am drawing here. So here you have the normal component. So see here the line AB, sorry, the line BC, which is perpendicular to the boundary. Okay, since the line BC is perpendicular to the boundary, so it is making a 90 degrees here. It is perpendicular to the boundary. We have to go with the normal components. We have to go with normal components. But here, see the normal components, how the normal components are there? So they are pointing upward. E2n is pointing upward. Similarly, E1n is also pointing upward. So I'm coming back here. E1n, so E2n is pointing upward. So similarly, E1n is also pointing upward. So see, B2C is going downward, but E2n and E1n, they are moving upward. So both are in opposite direction. Both are in opposite direction. So therefore, we have to go with negative sign for E1n as well as E2n. So therefore, if you apply this equation, that is closed line integral, line integral of BC E of DL. So if you consider this point as 0, so what will be the value? So integral 0b E of DL which is present. So this is if this is present in epsilon 2 plus integral from where to where, from 0 to c. So from 0 to c, which is present in epsilon 1 of E dl. So this value will be equal to, so for first one, so it is present in E2. So normal component is E2n. So but both are in opposite direction. The value is minus E2n. But what is the length from from B to 0? The length from B to 0 is delta H by 2. Delta H by 2. Next, coming with this equation, that is integral 0 C E of dl. So for integral 0 C E of dl, see here this remaining half part. So this remaining half part belongs to E1, but E1, which is the normal to the boundary, but the E1 component, which is exact opposite to that of the direction of OC. So therefore, this also we are going to take the negative sign E1n. And what is the length of this OC? The length of the OC is half part, that is delta H by 2. So this is our equation 2. So this is our equation 2. So equation 1 is, that is 1 minus E2n delta H by 2 minus E1n delta H by 2. So next we have to go with what? The third line. The third line is CD. The line is CD. So here I am coming back downward. See, we are having a boundary epsilon 2 E2, epsilon 1 E1, and whatever the line, the third line, which is nothing but CD, is present below the boundary. So this is CD, and its direction is like this. See here, this CD, which is completely shaded by which medium? Epsilon 1 medium only. So here the role of epsilon 2 is 0 on this line, on this conductor CD. So here this conductor CD, the width of this conductor CD is delta W. So therefore, if you do the integral from C to D of dl, the value is equal to delta W. But here you have one more value, that is E. What is E? Now you have to go for E1. And see, this conductor is in parallel with the boundary. In parallel with the boundary, we have to go for tangential component. We have to go for tangential component of what? E1. Tangential component is, the component is, so this is the diagram. So this is E1. So this is E1t, and the normal component, that is E1n. See here, the direction of CD is from right to left, but the direction of component, the tangential component of E1 is from left to right. So here both are in opposite direction. So therefore, since both are opposite direction, we have to go with the negative sign. Negative sign for what? E1t. Negative sign for E1t. So therefore, if you want to apply this line integral for CD of E of dl, so that value is equal to what? Minus tangential component of E1, that is nothing but E1t. Why we have taken the tangential component? Because the conductor CD is in parallel with the boundary. So therefore, E1t. And what is the value of integral dl? Integral dl is nothing but the length of the conductor CD. So what is that length? That is delta W, which is our equation number 3. Equation 3. And finally, we are going with the third, the last conductor. So what is that last conductor here? The last conductor is from D to A. The last conductor is from D to A. Here I have taken one boundary. Okay, the conductor is D to A and the direction is from D to A. And here the conductor A, I mean DA is in perpendicular with the boundary. So therefore, we have to consider which component? Normal component. But the line, the conductor line DA is shared by both epsilon2 medium as well as epsilon1 medium. So therefore, we have to consider E1 as well as we have to consider E2. So now, if I go with the component diagram, so this is E2 and this is E1. Normal component is like this and normal component is like this. I am not drawing tangential component because here there is no tangent. So therefore, this is E2n and this is E1n. Observe here the direction of this conductor is from bottom to top, and as well as the direction of E1n and E2n is also from bottom to top only. So both are having the same direction. So therefore, same direction E1 and E2 will be what? Positive. So here, but here we have to go with the half part is in epsilon2 and half part is in epsilon1. So that is what? Delta H by 2, and similarly it is also delta H by 2. So earlier what we have done in case of this conductor BC, similarly we have to go with the conductor DA also. The conductor DA. So for the integral of dA of E of dl, so will be what? Half is in epsilon1 and half is in epsilon2. So with respect to epsilon1, so what is the value epsilon1? So E1 n delta H by 2. So if you want, you can consider this point as 0. I can write like this: integral d to E of dl plus integral 0 to a E of dl. So this is equal to integral do of dl. The value is delta H by 2. And what about E component? The E component is E1n. So therefore, E1n delta H by 2. The component is positive, so therefore no problem. And next, coming to integral 0 to a, integral, if you do the integral from 0 to a, the value is what? Delta H by 2. So plus of delta H by 2, and the value of E in this medium is what? E2n. So therefore E2n. So this is our equation 4. So finally, we have got all the values for what? So integral a b c d a E of dl value, integral a b E of dl plus integral bc E of dl plus integral cd E of dl plus integral dA E of dl. So which is nothing but this is, so this is our equation 1. So this is our equation 2. So this is our equation 3, and this is our equation 4. So what is equation 1? So equation 1 is, so equation 1 is E2t delta W by, sorry, E2t delta W, E2t delta W. And what is our equation 2? So equation 2 is E2n delta H by 2 minus E1n delta H by 2. So minus E1n delta H by 2 minus E2n delta H by 2. What about the third equation? The third equation is minus E1t delta W by 2. So minus E1t delta W. And finally, what about the fourth equation? The fourth equation is here. So that is E1n delta H by 2 plus E2n delta H by 2. So finally the value is equal to 0. That is the equation now. So here the value is equal to what? 0 only. So this is the loop. So the value is equal to 0. Sorry for the disturbance. I can't do anything. That guy, he has just come to cut the trees. Anyhow, so please make concentration. So see here, E1 delta H by 2 and E plus of E1 delta H by 2 will get cancelled. E2n delta H by 2 plus of E2n delta H by 2 will get cancelled. So finally, the finally equation is E2t delta W minus of E1t delta W is equal to 0. So finally, E2t delta W is equal to E1t delta W. See here, one of the important thing I would like to tell here that you have to understand with respect to the concept. See here we are talking everything with respect to boundary. Everything we are talking with respect to boundary. So here, whenever the electron is traveling up to here, there is no problem. But when it comes to boundary and it is entering into the second medium, then only we have to go with the analysis part. So at the boundary, we have to check the conditions, boundary conditions. So everything we are talking with respect to boundary. See here we have taken one loop which is of delta W and the height is of delta H. When I am going to talk with respect to boundary, only if you look at boundary, only if you look the boundary, okay, so you can make the height of the loop can be 0. So at that time, if you look only the boundary, how, see earlier you have this boundary. Now I am looking only the loop with respect to the boundary means, so this is the loop. Whatever the value of A, B, C and D, so A will get coincide with D and B will get coincide with C. So therefore A, B will be here and B, C will be the here. So I'm looking only at boundary. So at boundary you can have only one line for which the value of delta H will be equal to 0, but delta value will not be equal to 0. Delta W will not be equal to 0. The width of the loop cannot become 0, but you can assume with respect to boundary, the delta H can be 0. So if so in this condition, so if delta W is not becoming 0, obviously in order to satisfy this equation, what E2t must be equal to E1t. So simply you can get cancel of these two, and I can tell what, so E1t is equal to E2t. But actually, what is the concept behind the this thing is here, since if at boundary, okay, so at boundary delta W cannot be equal to 0. So E1t, E2t minus of E1t should be 0 in order to satisfy this condition. Okay, so therefore here we have derived one of the important condition now. So what is that condition means? I am writing here E1t is equal to E2t. So from here what we can conclude? So the tangential components of electric field intensity, the tangential components of electric field intensity are being constant in both mediums. So whatever the value of tangential component which is present in epsilon 1 medium, it is also same in epsilon 2. You are making them as equal. So E1 to E1t is equal to E2t. So therefore, a tangential component, they are maintaining what? They are being constant. So therefore, these are known as continuous boundary conditions. Okay, so continuous boundary conditions. What are continuous boundary conditions? So that is the tangential component of electric field intensity for a dielectric medium is continuous. Okay, so now, so this is for dielectric medium. Now we have the relation between E and D. So that is what? D is equal to epsilon into E. So from where E value can be written as what? D by epsilon. So if you want to write it as what? E1t will be equal to what? D1t divided by E1. Because of it is E1 which belongs to epsilon 1 medium, you have to write it as epsilon 1. And similarly, E2t will be equal to what? D2t divided by, since it is E2 is epsilon 2 medium, so here you have to write it as epsilon 2. So as E1t is equal to E2t, what will be the value? D1t is equal to epsilon 1 and D2t is divided by epsilon 2. I told now we have to do the analysis for what? E and D. So here I am writing the conclusion for this. Both the mediums. So see here the tangential components of electric flux density, they are depending on epsilon values of the dielectric medium. So therefore they are discontinuous. Okay. So the electric flux density depending on epsilon values of the medium. So they are discontinuous. Okay, so these conclusions are important for us. So this equation and this equation. Here we have, just a minute, I think it will close. Here we have derived for only tangential components. So similarly, we have to go for normal components. ఇంకా అయిపోలేదమ్మా డెరివేషన్, ఇది సగమైనట్టు.